start the class. Okay, let me just arrange the notes as usual. Where is the this one? This one, yeah. All right, I think you can see my screen. Let me just send to you the AI video as well. Okay, this is the AI video. Let's see if I can open it. Okay, I think it's smooth. So let's start. Today's chapter is electronics. And we only have 3 drawers. So it's rather short, but this chapter, I have to remind you, it needs some calculations. The calculation exercise or activity that you need to know is more than the other chapters. So this calculation, I'll give you some concept to give you to help you to understand the entire principle or concept that you need to know for that drawer. However, in order for you to be able to understand and to familiarize with the questions, you need to do practice, because calculation questions is like maths or at maths. You need to practice more to be able to be familiar, right? But before you practice, obviously you need to know the concept, the principle behind it. You need to understand the fundamental. Once you understood, then trying to answer certain exam questions, it will be easier, much easier, right? So let's start. For this chapter, we have 3 drawers: electron, semiconductor diodes, and transistor. So I created the story. Ella says go. Then I start the question, do I go? In front, there is a traffic controller, and that is my sister, right? So Ella represents electron. Do I go? Sounds like diode, right? Diode. Okay. Do I go? Diode, right? And traffic controller is my sister, is transistor, right? So you have 3 drawers: electron, semiconductor diode, and transistor. So I hope this short story is able to help you to remember the drawer name in sequence. So now let's watch the story quickly. I'll just play. Right? Very short story because it is short. We only have 3 drawers, right? So let's start with step 2. Let me bring up the the clock. Okay, we will do 2 minutes to read from drawer 1 until drawer 3, which is temperature changed, right? So let's, again, I always repeat this statement for you to be familiarized on what is the expectation. So expectation is not for you to be expert after reading this. The expectation is just for you to go from level 1 to maybe level 2, right? Out of 10. 2 is the low, 1 is the lowest, 10 is the highest. All right, without further ado, let's start 2 minutes now. drawer 1 until drawer 3. You should be in drawer 2 or 3 now. Okay, you should be in drawer 3 now. Right? So there are 3 drawers: electrons, semiconductor diodes, and transistor. Right? And there are 3 key points over here for the electrons. I think if you haven't studied this chapter before, maybe these thermionic emissions sounds like a new terms to you. But don't worry, the answer or the explanation for this term is as simple as this. But we're going to go into more details in step 3 and step 4 and step 5. Right? Then you have this cathode ray. This is the experiment. Some of the school, they have the equipment that they will perform the experiment, so you can understand the experiment by experimenting it by yourself. If not, then you only have to, the only way that you can understand it is through your textbook, right? Your textbook is having the diagrams, is able to help you to imagine if you're doing the experiment, how it would look like. And then there's this energy conversion, right? So now we have done drawer 1. Then let's break down to drawer 2, semiconductor diode. So you have forward bias, you have reverse bias. This PN junction, don't worry about it right now. You're going to know it in more details as we go along to step 3 and step 4. Then you have this conversion from AC, alternating current, to DC, direct current, right? So then you have this half wave or full wave. There are different setup in the diodes that is needed to get a full wave or a half wave current, right? Then there's this capacitor. So capacitor is to smooth it out, smooth the conversion out, right? Then the transistor. So you have transistor. Transistor, you have emitter, base, collector, EBC. Then you have this very simple formula, which you're going to know it later more. You're going to know it. Then you have this application that is detecting the intensity of the light, whether it's dark or whether it's bright. Then you turn on the light, or turn on the alarm, or turn on the buzzer automatically. You don't need to go and switch it on by yourself. And also for thermistor is temperature. So for example, fire alarm. Fire alarm, once detected the temperature is high, that means hot, then they will turn on the fire alarm. Okay. So that's the 3 drawers. Okay, let me give you something extra today. Look at this. Right. If you have used ChatGPT before, Have you used ChatGPT before? I think you do, right? Right. Okay. So what I did is, you see, early in the morning just now, I uploaded the textbook. This is a textbook of your chapter 5, electronics. Then I asked it to break it down into 3 drawers. It's exactly as what we are going to learn this morning, right? So there are electrons, there are semiconductor diodes, there is transistor. Remember the 3 drawers, right? Then automatically, within a few seconds, ChatGPT created a summary, and that is break it down into 3 drawers. Electrons, which is drawer number 1. So you see they break it down into six points. If you can see over here, 1, 2, 3, 4, 5, 6, and those are the key summary that you need to know about thermionic emission, cathode ray, and effect of electric field, magnetic field, right, etc., etc. If you compare with the keynotes that I have, my keynote is only 3 points, right, compared to this 6. So it's really depending on you. Usually my keynotes is shorter. I try to limit it to about 3 or 4 points, because if it is having too many points, then it is no longer a short keynote that you can use it as a reference, right? Because I want it to be using it as a reference, like an anchoring point. So let's say if you go to drawer 2, it's the same. So you have forward bias, reverse bias, then you have rectifications, you have half wave, you have full wave, and you have capacitor, right? Then transistor, then you have this EBC, the 3 terminals. Then you have some information. The formula, remember the short formula that I told you is coming from here, right? This is the one, yes. So it's more or less the same, but this is a bit more detailed, right? So once you understand how brain drawer works, then it's easier, and with the tool of AI, it's going to help you to to create your own notes for other chapters or other subjects, right? Like I say, I'm teaching you the learning method, right? Don't see me as your chemistry tuition teacher or physics tuition teacher, because if you realize, I don't explain physics and chemistry as your regular as much your regular physics or chemistry teacher, because my point here is to help you, to guide you from step 1, step 2, step 3, step 4, step 5 until step 10. And by the end of step 10, which is about 2 hours, and we have done this many times, we are very sure that you will be able to understand this chapter well by testing the 10 MCQ, and usually I think you get 9 or 10 out of 10, right, out of all the chapter that we have done. So there is no doubt that you're going to, whether you're going to ask yourself this question, whether you're going to waste your 2 hours or whether you're going to make full use of 2 hours by understanding well on that entire chapter, right? So what I'm trying to say here is this AI tools, it could be ChatGPT, or there are some AI tools, Perplexity, Cloud, right? I'm using ChatGPT for this case, and it will be able to help you to study depending on how many levels you want to go into, right? I have step 1, step 2, step 3. You can, if you realize this for summary that is given by ChatGPT now that you are reading, right? That's moving right now. The detail is between step 2 step 3. It's more detailed than step 2, but it's less detailed than step 3, right? You can, what I'm trying to say here is you can actually break down to 20 steps if you want. And these 20 steps, for this case, this one could be step 2.5, right? Before you go to step 3. The more detail that the more step that you add into your layers, you will be able to read it repetitively on the same content, but with more details. Then you'll be able to increase your understanding higher, or more, right? So that is the concept of brain drawer, right? We are going through something that is simple, then going into something that is more details, so that you will not jump into something like you're reading a textbook. Most of the student, when they start opening the book and start reading a textbook, after 2 hours reading a textbook, they find themselves they do not fully understand what it is. If you try to do 10 MCQ, most probably you're going to get definitely not getting 10 out of 10, most of the students, right? Because straight away when they open the book, they jump into something very advanced that they have no understanding previously, right? So brain drawer is to help you to go through that stage, eventually to go to full understanding, but in steps，好像走楼梯这样，一步一步来，是吧？你一次过要跳去第10个 steps，就其实很难哦，除非你是跳高的冠军啊，是吧？大多数人都不是嘛。Alright, so that is the principle of brain drawer. Now, so going into step 3. Step 3, we have, let me see how long is this step 3. Okay, so we'll break it down into let's do 2 minutes for this drawer 1 until this table, right? If you realize this is the 1.1 thermionic emission and characteristic of cathode rays, they are similar, right? Similar, but the only for this page now 2 minutes. You should be in point 2 now. Okay, 10 seconds. All right, how do I read this? Is sometimes when you read the entire paragraph, you might not fully understand it. If you don't, then you can go back to step 2. And step 2 is giving you a short summary. It's easier to read and it's giving you the main message of that entire paragraph, right? So if you can fully understand this, then it's fine. If you don't, and you worried that you do not understand completely, and what is the main message that is trying to tell you, you can just refer back over. So that's why step 2, I always put it on the right hand side, even when we reach step 4, step 5, or step 6 later, because once you start to forget or start to be confused of what you have, what you are learning in this step 3 for this case, later you'll be step 4 or step 5, then you can refer back to step 2. Step 2 is like an anchoring point, right? Whichever point that you are confused, go back here and see whether you can find it. most likely you can find it. Then this short sentence will be able to give you more assured information that do not be confused. This key principle is is about releasing of a electron when it is hit on the metal, right? Okay. So same goes to point number 2, cathode ray, right? So till this 1.3, let's do 2 minutes. Let's start now. Okay, it should be in point 3. You can write down the formula on the paper if you want, because you might need this as a reference later. Of course, you can only also see it over here on step 2. All right. Okay, let's move to drawer 2. And let's set the expectation that your drawer 1 has improved or increased your level from level 2 to level 3. Right, level 3 is still a low level, but as long as you feel that you improve compared to 10 minutes ago, or when did we start? I think we start at, it doesn't matter, it's okay. Right, then it's fine. As long as you feel that there's improvement, then it's fine. So let's do drawer 2 for also 2 minutes, from drawer 2 until this one, 2.1. Okay, you should be reading the diagram now. Okay, let me do some quick explanation in case you need it. How do you read this diagram? This part is the battery, right? Battery, the longer side is positive, the shorter side is negative. And the current is flowing from positive to negative, right? So positive is this longer side and negative is the shorter side. So if you see the current is going from positive to negative, right? And with this closed loop, the bulb is able to light up, right? And for diodes, if you go from positive, diode also you have anode and cathode, if you see from this diagram, right? Anode is positive, cathode is negative, right? This explains the P-type and the N-type. The P-type terminal and the N-type terminal that you read just now in the step 2 on P and N junction, right? That is related to the P and N junction. So P is positive, anode, N is negative. So you can see, where is anode? Anode is here. Cathode is here, right? So when you move the current from positive to negative, you'll be able to light the bulb. But if you do it the other way around, you see the battery now is being flipped. Then there will be resistance. Why there's a resistance? Because that is the characteristics or there's a property of diodes. This gray color and this blue color rectangular box, this is diode, right? So that is the reverse bias. Okay, I think this is clear, and I hope this is clear. So now the full wave and the half wave is being, oh, there's quite some details over here. All right, so let's do 2 minutes. I'm going to scroll down as we read. I'm going to scroll down, let's say 2.2 for 2 minutes. Then 2.3, we're going to have another 1 minute. All right, let's do 2.2. Let's start now. Okay, we'll go to full wave. Just now was half wave, now it's full wave. All right, let me explain quickly because I think this diagram, if it is the first time for you to understand, to read, it looks terrifying, right? Let me explain a bit over here. The half wave, this one, you will create half wave. You remember the diodes? Okay, before that, let me take a step back, right? For AC, alternating current, for this cycle, the positive is like this. So it's positive here, negative here. So the current is going like this, like a clock, right? Like a clock, the clock direction. When the alternating current going into this cycle, the positive is here, the negative is here. So then it terbalik loh, terbalik into anti-clockwise, right? So clockwise, anti-clockwise, clockwise, anti-clockwise. So in 1 second, let's say this cycle is 2 seconds. So for the first second, it is clockwise. For the second, it is anti-clockwise. So it keep alternating. That's why it's called alternating current. Positive for the first second, then it will switch back to negative, positive here. Then the current will go like this, anti-clockwise for the second, right? So when you have a diode over here, you remember the diode will allow the current to flow if it is clockwise, because these are not discarded. When it turns to be from positive to negative, the other anti-clockwise directions, then the diode will stop the current from flowing. So it actually cut off the negative part. So that's why you have the output of this. So this is half wave. How do you generate full wave? That is going to look like this. This is the setup. Okay, half wave is this setup, very simple setup. Full wave is this setup, a bit more complicated. But once you understand the concept, and then when you have time later, you have to appreciate this diagram, and you start to follow the arrow, how this arrow works, with the understanding that this is AC current. So positive, then negative, then positive here as a clockwise. Then on the second, then positive here, negative here, then on the anti-clockwise, which is this one, right? Which is going to help you to generate full wave, right? So now that is half wave and full wave. Then this is half wave and full wave. This is full wave. You see the dotted line. And now how do we make it smooth as possible to make it like a straight line? This is how we use capacitor. Right, let's take 1 minute to read this 2.3. Let's do that. Okay, you should be reading the diagram now. All right, so let me just give a bit more explanation. This is spooling out the half wave. So you remember the half wave? We cut the negative cycle. And now if I need to smooth it out, I put a capacitor over here. And the symbol of our capacitor is like this. The difference between capacitor and battery is the length of this part, the horizontal line. For battery is one short, one long. For capacitor is they are same length, right? Then you can see it is trying to smooth out, right? Rather than having this shape. For the full wave, it's the same setup, but you added this capacity right in between here. And then the output is going to be like this. Okay. Then you might be asking, why do we need to smooth it out? Right? Why do we need to smooth it out? We're trying to convert AC to DC. AC is alternating current, DC is direct current. Direct current is the best direct current in the world is one line, straight line. One straight line. Right, one straight line. And DC is used to, for example, to charge your phone. Right, to charge your phone, you need DC. You cannot have AC because AC will destroy your phone. they keep changing your positive and negative, positive and negative, positive and negative, then your phone will be destroyed, the battery of the phone. Right. Same goes to other electronic applications, appliances. Right? That's why we are trying to make it as smooth as possible. Okay, so that is the reason. No. Drawer 3. Now we are going into drawer 3. Let me see how long is this. Okay, so we will also give you 2 minutes for 3.1. Let's start now. Okay, let me explain a bit. So now you understand that, I think you understand that there are two type of transistor, NPN and PNP, right? Usually you'll be using NPN. PNP is not that normal compared to NPN. Why? Okay, before I answer the why, let me show you the diagram. So this is NPN, this is PNP. What is the difference? The difference is the flow of the current. NPN is from collector to emitter. Collector is here, emitter is here. Right. Remember, we have 3 terminals in the transistor: emitter, base, and collector. So you have emitter is here, sorry, emitter, then you have collector, then you have base, right? So you have 3 terminals. And for PNP, is the flow of current is opposite. It's opposite, right? So what they are doing right now over here is, if you realize, there are 2 batteries over here. There are 2 switches, right? Once you switch these circuits on, then these circuits will you'll turn it on. Right, this circuit will turn on. Once you switch this circuit on, this circuit will turn it on. Right, and this circuits here, the base to emitter, is a small current. So you use a very small current to turn on a very big current. Right, so the objective of transistor is like an amplifier, amplification. Okay, so if you do not fully understand and you do not know why we are still learning transistor, don't worry, because we are still in step 3, level 3. So you just need to know that there is this NPN, PNP, and then there are 3 terminals, emitter, collector, and base. And then you will know that there is this formula of gain with a small current to turn on big current. Small current, turn on big current. That's it. That's it. You need to know for now. Right. Later you're gonna understand much better. Right. As you're going to read this further. So 3.2 to 3.3, we'll do 2 minutes. I'm going to slow down a bit for to show you the diagram later. Okay, let's start now. 3.2. Okay, 1 more minute. All right. So this transistor, there are two types of applications. LDR, light dependent resistor, and thermistor. LDR is when it's dark or bright, then it will do something. Turn on the light or turn on the fan, right? And thermistor is when it is related to temperature. One is related to light, one is related to temperature. Different temperature setting, then it will automatically turn on something, right? You do not need to go and manually go and press or turn on the switch. Okay. Now, let's do this very quickly for 1 minute. Let's read this step 2 again, and I hope that you feel that you understand it more now compared to maybe 20 minutes ago when you started reading this. Let's start now. Twenty seconds. Okay, for this chapter, so far we have been a bit slow. From now, we were going to start faster. I think you understand well on these three drawers after having step 2 and step 3. So now let's go to step 4. Right. Step 4, we have 2 questions per drawer and 2 questions. Yeah, no, some are 3 questions, but in total, I think there are 8 questions. So let's read question 1 for 1 minute. Right, 1 minute I think is enough because now I think you already have a good understanding about what is draw 1. Let's start now. 10 seconds. Okay, let's go to question 2. Also 1 minute. Okay. If you have time to read question 1 again, then let's do it after question 2. Twenty seconds. All right, let's go to question 3. Let's start 1 minute. Twenty seconds. Okay, I hope your level increased to level 4 for drawer 1. Let's do drawer 2. I'll give you 1 minute for question 4 in case you want to continue with question 5. You can do it. I'll give you 1 more minute. Then you can continue to question 5. Okay, the second minute starts now. Okay, I hope you're, oh no, still one. Okay, let's do 1 minute for question 6. right? So let's go to drawer 3, and I hope drawer 2, your level is increased to level 4. Okay, let's do 2 minutes for question 7 and question 8 together. One more minute for question 8. Okay, question 9, last one, 1 minute. Okay, so let's continue on step 5. Then only we'll do this review again. Okay, step 2. Now I hope your understanding for this chapter increased to level 4. Level 4 is you should be getting 4 out of 10 question correct. Right, 4 correct question, correct answer out of 10. Now, the step 5, let's see how long is this. Okay, we will divide them into two parts. So let's take 2 minutes for this draw 1 until this part of point number 2. Okay, I think by now you know thermionic emission quite well. Now, point number 2 is about the characteristic of cathode ray. There's one table. Okay, let's read this in 1 minute. Then we'll go read the table until this point number 3 in 1 minute is enough. Okay, let's try 1 minute. Then let's see. Okay, I hope it's enough. Okay, remember this Fleming left-hand rule? We learned it in the previous chapter. This is chapter 5. That is chapter 3, electricity. Right. If you do not remember, that means your level 9 that you gain maybe 1 month ago decreased to a lower level. Why? Because you did not perform the revision. Right. You have to revision is not just 1 time or 2 times. You have to do it constantly. But I think you know the revision steps. So if you want to improve yourself back to level 9, you know what to do. Right. So let's do 1 minute for this part. Just appreciate the formula. All right. Now let's move to drawer 2. Let's do drawer 2 until this table for 2 minutes. Let's start now. Oh yes, before I go further, I just suddenly thought of one thing. For example, if you have any points that you are not very sure, you can do like this. You can do a screenshot, or you can just type it out or copy and paste and go to, remember this ChatGPT. I'm assuming that you know what is ChatGPT and you have used it before, right? Then you can put it like this and explain in a simpler way to me, right? Then he'll give you all the explanation as simple as possible for you to understand, right? So this is just another way for you to understand if there's any particular part in the notes, for my notes, or for any reading materials that you are reading. You can just ask the ChatGPT, right? Just like he or she is your friend and an expert who knows everything. All right, let's do 2 minutes for 2 and 3. Let's start now. You should be on 3 now. Twenty seconds. Okay. Yeah, for example, this, the diagram where you have D1, D2, D3, D4, the diodes to make it a full wave. At first, when you read it or when you see that diagram, it looks quite scary, right? So what you can do is also you can copy that screenshot and put it into ChatGPT and ask ChatGPT to explain to you, rather than you trying to figuring out by yourself. Of course, you're still able to figure out because it's not so difficult, but it will take more time. Maybe it will take half an hour or even more to understand the flow, to understand how it works, to understand how this diode is being reacting to creating the full wave. Yeah, once you set it into ChatGPT, then it will be able to explain to you in full details, and it's easier for you to read it and to understand. Right. So that's also another way for you to do that. Right. Just in case you are interested to have the wait, let me show you. Have all the notes. Yeah. If you're interested to have all the notes, I upload it into this Google Drive. You can click on it, then yeah, you can get all the notes. Okay. The other link that I'm sending is the YouTube. In case you are lazy to read and you want to uh, rewatch the classes, then you also can do that as long as you have 2 hours. And I think that after the 2 hours, you go back to level 9, right? Because every time we do that, you did it successfully. Now let's continue on drawer 3, and let's see how long is this. Okay, it's just a little bit. So let's do 2 minutes. I'm going to slow down a bit more to cover the entire drawer 3 transistor. Okay, you should be in 0.2 or 0.3. Let me scroll down a bit. Another new scary equation for 0.3. All right. Okay, this equation, if you think that it's scary, also you can do the same thing, right? You can just screenshots and just put it into the ChatGPT and ask the ChatGPT to explain to you in a simpler way. Then it will give you all the explanation that you need, right? You can keep asking questions until forever. Now, let's move on. Okay, before we move on to step 6, let's take some time to read this step 2 again. I need to have the feeling that you are you understand this chapter way more than maybe 1 hour ago. Right, let's do 1 minute. As long as you have that feeling, then it's fine. Then you achieve the objective. All right. I hope you are able to achieve that feeling that you feel that now you understand way more than 1 hour ago when you started reading this, right? Now let's go to step 6. Step 6 is the story for each drawer. Now, let me tell you the story that I created. You can create your own story as long as it makes sense to you, right? Drawer 1, electron. Electron, the first story is under hot sun, Dominica attracted and traveled in vacuum with momentum to anode. So Dominica is attracted to anode, right? And then she traveled in vacuum with momentum, right? So how do you explain this story? I think by reading this story, I think maybe you already have some idea why I use hot sun, why I use Dominica, attracted, vacuum, those keywords, momentum and Arnold. Let me explain to you in my thinking, how do I create the story and why do I create this story is under the hot sun. So thermionic emission, you need to have a heated metal, right? Once that heated metal that is related to hot sun, and Dominica is to help you to remember these terms. I think this term for now, maybe you can still remember. If you do not use it, or if you do not practice it, revise it long enough, you definitely forget these terms because this term is not common. So I use this term Dominica to help you to remember this thermionic. Dominica thermionic sounds a bit similar because it's hard for me to get thermionic that sounds similar. If you are able to find one, then just replace Dominica with the term, whichever terms that you like. Or if you think thermionic sounds easy to remember, then just put thermionic. Somebody's name called thermionic and he's attracted to Arnold. Dominica is attracted to Arnold, and then she traveled in vacuum with momentum. Right. I think you also know why I put a vacuum over here, right? To help you to remember that during that experiment, you require a vacuum to avoid collisions of the electrons, right? Then momentum. So the electrons are travel in straight line, okay, and having momentum and energy, right? So that is drawer number one. Story for drawer number one. Let's go to drawer number two. Arnold is Mr. Positive. Kathy is Miss Negative. They are both driving into two speed bump. The first has two bumps, so they are in two speed bumps. The first has two speed bumps. Usually speed bump is one, but for this case, Arnold and Kathy, when she's driving on this road, let's say in Pelangi Indah, and this bump has two bumps. This speed bump has two bumps. Then soon after that, they reach another bump, and that bump has in four bumps. Right, and then there's a capybara hide between the bumps. Okay, I know it's a silly story, but that is the point. We need to create emotions for you to be able to have this long-term memory. So Arnold, I think you know what is this. For drawer number two, we have this Arnold, which is positive, and then we have cathode. Cathode is I represent it as KT, which is negative. And they drive into two speed bumps. The first one has two bumps, and the second one has four bumps. So this is talking about the half wave and the full wave. Right? You remember the graph? The half wave is having two bumps, and the full wave is having four bumps. And then capybara is representing the capacitor. Right? Sounds like capacitor, capybara, hiding between the bumps. So capacitor hiding between the bumps, so they smoothen out. The capacitor is to smoothen out the output of the wave, right? So that is the story. Story number three, transistor. How do you remember this? Bob, Kathy, and Emily. So these the three terminals, base, collector, and emitter, go to noon party. Why noon party? Because NP. Right, remember I told you we always use NPN, noon party until night. So these three friends, they went to a party from noon until night. So noon party until night, NPN, right? Police use amplifier, ask for IC, ask from Bob. Right, so police, they use this amplifier, this loudspeaker, and ask Bob for his IC. Right, and then in this party, the more dark and the more cold, the more people. Why is dark and cold? The more dark, then it will, for this LDR, it will light up the buzzer or the light. All right, the more dark. And the more cold, if it is too cold, up to a level, then something will turn on. The heater will turn on, right? Or the light will turn on, or something will turn on. Okay. So this is to help you to remember there is this LDR and thermistor in the applications. Right. So let's watch the video, the short video, so that it will. I hope that it will help you to remember the story inside each drawer. Let's start from the main story again. Let's start now. It's only less than 1 minute. All right. So this is the picture. The picture to help you to remember the story. So we have the AI video, the animated video, to help you to remember the story. We also have a simple picture that I draw to help you to remember the story. So this is Dominica attracted to Arnold, going into a vacuum, and also with momentum. Then Arnold and Kathy, they are driving in a car, and they got two speed bumps. One is the speed bump that's having 2 bumps. One is the speed bump that's having 4 bumps. I don't know how to draw capybara, so I put a capybara here. So hiding in between the bumps. Then transistor, you have this Bob, Kathy, and also Emily. Right. Then they went to this noon party from noon until night. Then there's this policeman asked for IC for Bob. Right. So this IC for Bob is to help you to remember the formula. You know, the formula, the IC divided by IB is current for the base and current for the collector. So this is to calculate the amplifications factor, right? Then this is the transistor, and this is the formula to calculate if it is thermistor or if it's LDR. And when it is dark, then you will turn on the light. When it is cold, you will turn on the maybe heater or alarm. It cannot be too cold in that room, for example. Right. So that is step 6. That is step 6, which is to help you to remember the keywords, not in terms of text, but in terms of vision. Because human can remember based on vision more than text. Right, more than text. I think this video, if that video that we saw just now, less than 1 minute, if you watch this more times, maybe 10, 20 times, it's only 1 minute. If it is 20 times, it's only 20 minutes. It will be, I think it is much easier for you to remember the story in 20 minutes by just watching the video, rather than spend the 20 minutes and trying to remember all these texts. Right. And why this video, why this drawers, why this story is being created is to help you to remember the key information inside each drawer. Once you know this key information, this is going to be the anchoring knowledge for you to know what is inside this chapter. Okay, first what is inside this drawer, then extend it to what is inside this chapter, because drawer is a subset of the chapter, right? Now let's go to step 7. Step 7, then we'll go to step 8. How do you do step 7? Okay, I'm going to repeat myself. Read this question, make your own answer first. Based on the reference, I'm going to put this as here. If you have jotted down some keynotes or some key information on your piece of paper, you can also use that as a reference. Then only you start to compare your answer with the answer. All right, this is to train what? Train the how fast you can retrieve information from your brain. right? And then also train the discovery. When you discover new things, new answer that you do not have, then intentionally pick it up and put it inside your drawer. Right? This is to train two things. So now let's do 2 minutes from drawer one, question one until question three. Let's do it now. Thirty seconds. You should be in question three now. All right. So drawer one, your understanding level should go to level 7 now. If I give you 10 questions, you should get 7 correct. Right. And drawer one, let's go to drawer two. Diodes. Also 2 minutes for the 3 questions. Let's do it now. Well, 1 more minute, you should be in 5 or 6 now. All right. We are going to 7, 8, and 9. Let's do 2 minutes. Start now. Okay, this question number 10. Let's do 1 minute. Level 8. The video usually give a big boost. I don't know whether you have the same feeling. Able to watch and hear the video? Just to make sure before I continue. I'll play the video again. Are you able to hear the video and watch the video? Siling, are you able to? Siling, are you still with us? No? Okay. You think you're lagging? Okay, let me share again, just to make sure. Okay, what about now? I'll play the video now.
How big invisible physics skills power these systems. Okay, let's dive into this. Here's our roadmap.
Are you able
1.
to
Freeing
watch
the
the
electron.
video?
2. Diodes and directing the flow. And 3. Transistors, the electronic brain. By the end, you'll see
You can hear, but can you watch? Can you see it?
exactly how all these building blocks fit together. All right, part 1, freeing
Okay, good. So let's do it from the start. 7 minutes, start now.
Hey everyone, welcome back to The Explainer. Today, we're going on a bit of a journey. We're literally tracing the path of a single freed electron and following its evolution all the way up to the very foundation of the digital revolution. Let's unlock the pure physics that absolutely makes our modern world possible.
You know, when you think about the massive systems running complex artificial intelligence, or say autonomous vehicles today, it almost feels like magic, right? We kind of take all that macro-level complexity for granted. But today, I want us to look underneath the glass and metal to see exactly how microscopic, invisible physics scales up to power these massive systems. Okay, let's dive into this. Here's our roadmap. 1. Freeing the electron. 2. Diodes and directing the flow. And 3. Transistors, the electronic brain. By the end, you'll see exactly how all these building blocks fit together. All right, part 1, freeing the electron.
So, first things first, how do we actually get our hands on a free electron? Well, we use something called thermionic emission, and it's exactly what it sounds like. We're using thermal energy, heat, to emit electrons. Picture a tungsten filament just packed with buzzing electrons.
If we apply just a simple 6-volt power supply, its temperature absolutely skyrockets. We're talking over 2,000 degrees Celsius. That intense heat gives those electrons so much kinetic energy that they literally jump right off the metal surface.
Now, once these little guys are freed in that we call cathode rays, and here's where it gets cool. Because they're negatively charged, they don't just shoot in a boring straight line. They can actually be steered by magnetic fields or deflected toward positive plates. Plus, they possess real momentum and kinetic energy. In fact, this exact process is what was used to literally draw moving pictures onto the screens of those old super heavy CRT televisions we used to have. And this brilliantly illustrates some incredibly clean physics. You heat the metal cathode, you emit the free electrons, and then you accelerate them toward a positive anode. And because this whole thing is happening in a vacuum, there's zero air molecules getting in the way to slow them down. So all that electrical potential energy is perfectly converted into maximum kinetic energy. It is just this flawless, elegant conversion from potential right into motion.
Moving on to part 2, diodes, directing the flow. Okay, so having high-speed electrons flying around is great and all, but if we want to build useful electronics, we have to bring some order to that chaos. Enter the semiconductor diode. This is our ultimate traffic controller. It features what's called a PN junction. Basically, that's a boundary made of positive and negative semiconductor materials, and its purpose is an absolute game changer. It acts as a strict one-way street. It allows electric current to flow through in one direction, but physically blocks it from going backward.
So the crucial point here is how this junction reacts to polarity. When it's forward biased, which just means the current is pushing in the allowed direction, the diode's internal depletion layer thins out. The resistance drops to almost zero and current flows freely. But if you reverse that bias, that depletion layer suddenly widens. The resistance absolutely spikes, slamming the brakes, and the current stops completely. It's essentially a perfect solid-state valve.
Now, you might be wondering, why does this one-way street even matter? Well, it's all because of a process called rectification. That's the process of converting an alternating current, which surges back and forth, into a direct current that flows in one straight line. Think about it. The wall outlet in your house provides this messy alternating AC power. But the delicate battery in your smartphone, it absolutely requires steady DC power to charge safely. So diodes act as that critical bridge, rectifying that alternating cycle into one single usable direction. But here's the catch. Rectification alone leaves us with a pulsing, kind of bumpy direct current. And delicate electronics really hate bumpy power. So we have to introduce a smoothing process. And we do this using a capacitor. Here's how it works. Alternating current enters the circuit and the diodes rectify it into half-wave or full-wave DC, the voltage pulses up. When it does, the capacitor acts like a giant sponge, charging up as the potential difference increases. Then as the potential difference tries to drop, the capacitor discharges. Smooth, steady line of power.
All right, which brings us to part 3, transistors, the electronic brain.
So we've got smooth power, right? But now we need logic. We need the system to actually make decisions. A transistor is remarkably simple in its structure. It's made up of 3 parts, an emitter, a base, and a collector. Honestly, the best way to think about it is like a water faucet. The emitter is your main water supply, providing the charge carriers, and the collector is the giant drain receiving them. That very thin middle layer, the base, that's the knob. By applying just a tiny bit of force to turn that base knob, you can control a massive rush of current from the emitter to the collector.
Now, there are 2 main physical flavors of these components, NPN and PNP transistors. The primary difference here really just comes down to their semiconductor structure, whether they have a P-type or N-type base, and the direction that controlling current flows. For an NPN, it flows base to emitter, and it's reversed for a PNP, emitter to base. The underlying physics doing the work is exactly identical. It just changes how you actually wire them into your specific circuit.
0.7 volts. I want you to remember this number because it's kind of like a magical threshold. With a standard silicon transistor, you don't need some massive power surge to turn that knob we just talked about. You literally just need a tiny minimum base voltage of 0.7 volts to wake it up. The very second you hit that exact mark, the gate flies open, and it turns on that much larger collector circuit.
Let's move on and see how this builds into something incredible, the amplification process. You apply a tiny whisper of a voltage to the base. That tiny base current flows, and it immediately triggers a proportionally massive flow of collector current. So the input signal gets drastically magnified. Think about a singer at a massive stadium concert. The tiny little electrical signals from their microphone go straight to the base of a transistor, triggering a huge rush of power from the main supply out to the massive stadium speakers. It perfectly magnifies the exact same waveform so everyone can hear it. But it gets even better, because beyond just amplification, transistors can act as automatic switches. They essentially make automated decisions based on their environment. For instance, pair a transistor with a light-dependent resistor, or LDR. As the sun sets and it gets dark, the LDR's resistance shoots up. This redirects the voltage until it hits that magic 0.7 volt base threshold we mentioned. Boom! Instantly, your city's streetlights automatically turn on. Or swap that LDR for a thermistor. If a room gets too hot, the thermistor's resistance drops, hitting the threshold and triggering a fire alarm. This right here, this is the literal physical bedrock of our modern automated world. Now, what's really fascinating about all of this is the scale. We started today by looking at a single freed electron just jumping off a hot wire. Then we saw how to direct it with diodes and amplify with transistors. Today, we are cramming literally billions of these microscopic switches onto a single chip the size of your fingernail to power advanced artificial intelligence. So as these foundational building blocks continue to shrink and scale up in complexity, how will this invisible physics shape the future of our sustainable automated world? It's pretty mind-blowing to think about. Thanks for joining me on this journey, and I will catch you in the next explainer.
All right, so that is step 8. I think step 8, after watching the video, if you put in attention, your focus on watching it, I think this will help you to solidify what you have learned for the past 1.5 hours, right? Let's make it even stronger by listening to this very short podcast. Okay, I'm going to highlight the part.
Welcome to this
that
deep
they are
dive.
talking
Today,
about.
we're pulling from a really fascinating physics source text on electronics.
Yeah, it's a great one.
And our mission here is to trace the incredible journey of the electron for you. You know, going from its raw state, flying freely in a vacuum, all the way to becoming the invisible building
Oh,
block of
before
your...
that, are you able to listen to the lady and the gents? Because I'm playing a podcast now, right now. Yes, okay, good. Let's continue.
Smartphone, AI, the whole digital revolution.
It's essentially a story of taming the subatomic world.
Yeah.
And chronologically, the text starts with thermionic emission.
Right.
Because to get electrons to do any useful work, well, we first have to liberate them from the metal atoms they naturally orbit.
Yeah, the source text talks about heating a tungsten filament to give those electrons enough kinetic energy to break free. I kind of view it less like boiling water and more like, I don't know, achieving orbital escape velocity.
I mean, that's exactly what it is. You pump in thermal energy until they cross that threshold.
Notice a neat trick in the text. They coat the tungsten with barium oxide.
Yes, that barium oxide layer is crucial. It significantly lowers the energy barrier, what we call the work function, meaning you can achieve that electron escape at much lower temperatures. It saves a massive amount of power.
Okay, so once they're free, the text moves them into a vacuum tube and applies an extra high tension, or EHT, supply.
Basically, a really high voltage.
Right, which accelerates the electrons into high-speed beams called cathode rays. Now, the source makes a pretty bold claim here. It says this is a perfect energy conversion. Electrical potential energy transforms entirely into kinetic energy.
Yeah.
But I have to push back a bit. I mean, in physics, nothing is perfectly efficient. Where's the loss?
Normally, you'd be totally right to be skeptical. But the vacuum environment is the secret.
Oh, because there's no air.
Exactly. The tube is evacuated, so there is literally nothing for the electrons to collide with. No friction, no heat loss to surrounding gas. So that conversion from potential to kinetic is, well, for all practical purposes, completely direct.
Oh, wow. Okay. That makes sense. But obviously, vacuum tubes are fragile, bulky glass jars. You can't exactly put them in your pocket.
No, definitely not.
So the narrative logically shifts to solid materials. We had to figure out how to direct electron traffic inside a crystal lattice, which brings us to the semiconductor diode.
Right, and specifically the PN junction. You take a P-type material.
Well, the one with the positive holes, right?
Exactly. And you join it to an N-type material, which has an excess of free electrons.
Which, honestly, I've always found the concept of a hole so counterintuitive. We're treating an empty space as if it's a moving physical particle.
It is a bit of an abstraction, yeah. But mechanically, it works. When an electron moves to fill a void, The void effectively moves the other way, and where these two materials meet, electrons and holes cancel each other out.
Creating that depletion layer.
Spot on.
Yeah.
Now, if you apply a forward bias voltage, you force that depletion layer to shrink and current flows.
But if you apply a reverse bias, the layer expands. It becomes a massive roadblock. So it's basically a one-way turnstile at the atomic level.
Yes, which is the exact mechanism we use for rectification.
Right. Taking alternating current from the wall and turning it into direct current for your phone.
Right. You take 4 of these diodes, arrange them in a bridge, and force that oscillating AC into a one-way DC flow.
But that raw DC isn't perfectly flat, is it? Doesn't it pulse?
It does. It's very bumpy. And delicate microelectronics need perfectly smooth voltage.
Which is where the capacitor comes in. It's wired in parallel.
Exactly.
I picture it kind of like a heavy flywheel in an engine. When the voltage surges, the capacitor charges up and stores the energy. When the voltage dips, it discharges, filling in the gap. It smooths the chop into a steady stream.
That is a great way to visualize it. So a diode acts as a turnstile, but to build a true brain, you need the transistor.
Because it adds a third terminal.
Right. Structurally, we now have the emitter, the base, and the collector. And the magic here is that a tiny current at the base modulates a massive current flowing from emitter to collector.
Which is amplification, like taking a tiny signal from a microphone and boosting it to fill a stadium.
Exactly. A minute fluctuation creates an identically shaped but enormously magnified output.
Yeah.
And beyond that, it gives us automatic switching.
Right, like if we use a light-dependent resistor in a potential divider circuit, in the dark, the LDR's resistance spikes.
Which alters the voltage.
And that triggers the tiny base current, unleashing the main current to automatically turn on a street lamp. Or a thermistor doing the exact same thing for a fire alarm.
You're using the physical environment to dictate the logic of the circuit itself.
It's just brilliant. We've gone from ripping electrons out of hot metal to directing them through crystal turnstiles to giving them logical switching power. Every smart device you own is built on this exact sequence.
Every single one.
But it does leave you with a somewhat haunting physical problem. Modern chips pack billions of transistors into microscopic spaces.
We are rapidly approaching the absolute physical limits of the universe.
Yeah, transistors are becoming just a few atoms wide. So what happens to the digital revolution when quantum tunneling kicks in and we literally cannot make these components any smaller?
Will the electron finally refuse to be tamed?
Definitely something to think about the next time you hold your phone. Welcome to this deep dive.
Right. So I hope you find it interesting. Right, then we go to step 10, the last step, step 10. Right, before we go to step 10, let me just explain to you in 1 minute one thing that is in my mind. After getting through this step 10, I'm sure you're going to get, again, 9 out of 10 or 10 out of 10, right? But if you try to do your past year questions, you feel that you do not get 10 out of 10 most of the time. Reason is because this question that is being provided to you now, they are not the exam level questions. They are the question to test your understanding. So to get 10 out of 10 or 9 out of 10, that shows that you understood the chapter well. You understood there is electron, you understood how it works, you understood the thermonic emission, you understood diodes, you understood the PN junction, you understood the full and half wave, and also you understood transistor. But to be able to answer exam level questions, you need to practice, right? You need to practice exam questions. So do not be worried if you started to do past year question and you feel that why I'm 9 out of level 9. I feel that I'm level 9, which means that I'm supposed to be answering, to be able to answer the exam question well, but I did not have that ability yet. Because, like I say, the question that we tested you on this MCQ is it's not the exam level questions. It's a question to test whether you understood the chapter well fundamentally. Exam level question is another type of, some of the questions are different. They ask you in different way. So you need to be familiarized, right? You need to be familiar with this exam question. But once you are having a strong fundamental, for strong understanding about the chapter, then getting or learning from the exam past exam questions with the answer, it will be easier, much easier, right? Okay, let's start now. Question number 1. What is the answer? We're gonna have 10 questions. Okay, I'm waiting for you. You're typing. Yep, I think so too. Okay, question number 2. All right. Number 3. I think so. Yep. Number 4. Drawer 2. I think so. Yep. Number 5. I think so. Yep. Okay. Yep. Me too. Number 8. Good. Very good. Number 9. See, yes. Last one. Transistor. Yep. 10 out of 10. Excellent. Like usual. Okay. So good luck in you becoming exam ready. Right. This 10 out of 10 is not exam ready yet. Okay, Singling? I know I repeat this like 200 times. And I know you have already understand this like 300 times. But why I keep repeating this, because this is extremely important. This is extremely important. You need to be exam ready to be able to get a good result in your SPM, because SPM is all about exam. SPM is not just about understanding it at the fundamental level, right? You need to know how to calculate. You need to know how to answer the right answer that the examiner want to see, right? With the keywords, right? Okay, this, like for example, this one, they are formulas. This one need to do some practice about the calculations. You understand the concept already now, but doing calculation is another level. It's a bit different, right? So in 2 hours, I will not be able to help you to be exam ready. But to be exam ready, you need to put in more effort to be ready. All right. So let's have a break and see you later in the second class, chemistry chapter 3, form 4. Thank you. Bye bye.